Hello, Fahima. Hello. Uh, Hello, Tilak Kumar. Hello.
Good evening, sir.
Hi, Netrasri. Can we wait for 5 more minutes such that if any students can join, we'll
Yes,
wait for few more minutes. Okay, thank you.
sure, sure, sir.
Yeah, I think there will be less attendance, so we'll start the class and we will see if somebody joined, then we can see. Uh, am I audible? If can any one of you can tell me that if I am audible, then I will continue.
Yes, sir.
Okay, sure, thank you. Basically, in today's session, I am going to discuss about the few topics of the week one. As the week one assignment is week one and week two assignments are already been given for the given out in the NPTEL videos. So today it will be like overall it will be like a orientation session, and in this orientation session what I will teach you was like the basic concepts of thermodynamics, which was covered in the first week, and followed by that in the next week I will teach you the second week concept, which starts from the Maxwell equation, Gibbs-Duhem equation. Yeah, so one second, let me show you the share screen. So are you guys able to see my screen? Can somebody tell me that whether you can see my screen or not?
Yes, sir.
Okay, fine. Thanks for the response. So basically today's session will be on the problem solving session with slight overview of what do you call overview of the topics which was covered in the week one. So today it is basically like the course name, you all know that it is a thermodynamics for biological systems, classical and statistical aspect. Before going into the topic, I want to introduce myself. I am Ganesh Reddy from IIT Patna, who was a PMRF candidate, uh, which I obtained in the year of 2022, and my ID is 2703565. And my research area is mostly on the modeling of protein simulation. If I talk about the protein simulation, uh, basically what I will do was, say suppose if you get any drugs, the best suitable example was recently they have developed a drugs for the lung cancer, breast cancer. Basically my work will be overall related to the drug design part. uh, when I'm talking about the simulation, or what do you call the drug design, uh, so basically when you are talking about the thermodynamics, I will include how my research is inclined to the thermodynamics, then we will start the research topic. So basically in the research field, when you are talking about the modeling of the protein systems, or say suppose a drug design, what we will do was, we are not considering the motion of the particles, or the what is the translational motion of the particles. We'll consider the, say suppose the bonded parameters, non-bonded parameters, and which was totally known as the internal energy U, which is similar to the internal energy which you have, and we will use the classical MD approach, the first part of this approach, the classical thermodynamics, to study the properties of the protein and the drug design. Here we are not creating, not destroying anything. We are transforming the energy from one form to another. Uh, I will explain that in the subsequent slides. So without any further delay, we will go into the topics of this today's session. Initially I will give you the overview of the thermodynamics, and then later I will showcase the 2-3 example problems on how to do the first week assignment. Say suppose that whenever we talk about the thermodynamics, we have the system followed by the one second, if I can write it. Yeah. So we have the system, and then followed by the surroundings, and we know the boundaries, right? So if you know well better about the system, surroundings, and boundaries, can anybody explain me out of you two, if it possible? What is your understanding of system, surroundings, and boundary? So basically, sorry. Yeah. Basically, system is the one. Say suppose we have the thermo flask, which we have the coffee in it. Can you give me the example of system surrounding and boundary in this case? Say suppose I have the thermo. Wait a second, somebody's. One second, somebody's joining. So can you give me the example of like say, what do you mean by system surroundings and boundaries? With the example of thermo flask, if I say that, say suppose I have the thermo flask. Uh, Say I have the thermo flask with coffee in it, and there is surroundings. So can you give me the example of like which system it will be like? What is the system here, and what is the surroundings, and what is the boundary, if it possible? So yeah. So am I audible, right? Hello. Hello. Am I audible? If anyone can respond.
Yes, sir.
Yeah. Thank you. So when I'm talking about the system surroundings and boundary, why we are discussing this was, so this is the basic element in the thermodynamics where it is very useful to understand at a very concern that what is the system and what is the boundary and what is the surroundings. So if I given the example of thermo flask with a coffee in it, the thermo flask which acts is right, the liquid which is inside it will be considered as a system, and the outside one it is considered as a surroundings. So and the properties which are inside are there, right, that are known as the particles or variables, what will go further that. And here we have that insulator, right, which acts in the thermo as a thermo flask. It acts as a, what do you call, the boundary. So yeah. So once if you go there, so now we have, I have told you that how can you define the system and the surroundings. Say suppose another example of system and surroundings is the human body itself. We are the human bodies which consist of a n number of particles. Say suppose we have the blood, water, the proteins, and the every system in our body. And outside our bodies, everything is surroundings to us. And the another best example is, take a room. And take any corner, and say suppose you, out of the room, you take one certain brick of the room and say that, okay, I am focusing on this only one brick, and that brick will be known as the system, and the following the remaining part which is carried out by that is the surroundings. So when I am talking about the system and surroundings, there are three types of systems, I mean, in the notation wise. One is open system, closed system, and isolated system. uh, Before giving the definition of open, closed, and isolated, I can tell you, like say suppose, I have given the example of two examples. One is body, another one is the thermo flask, coffee in the thermo flask. And I can give you another point. Say suppose the water bottle with, say suppose you bought the bottle with cold water. Uh, so there are the three different examples we have. One is the human body. Otherwise, I can say it as a hot water in boiling water, uh, where you are boiling the water in the open lid. And the another example is the cool water in the water bottle, and the third example is the thermo flask. So to put it in the good words, the open system will be there where it can transfer the mass and energy. Say suppose, if I take the human body, we can transfer it, right? Say suppose we can transfer the sweat on our body. It is transferring from the system to the surroundings, and even the energy also. Say suppose if I take the boiling water in the open lid, where the water is converting into the air in the surroundings in the form of the droplets, gases, molecules. So that is another example of open system. And if I talked about the closed system, say suppose we have taken the water bottle with cold water in it, the normal water bottle. So after some time, the mass of the water will be the same. The how many molecules of water you have in the water bottle will never change, irrespective of how much time you kept it in the bottle. But the transfer of energies happen from the inner bottle to the surroundings. So if you can see that, if you bring the bottle, once you get it into the outer side, the water bottle will lose its, what do you call, the coldness, and it become warm because it transferred the energy from the inner system to the surroundings. And to come the example of isolated system, the best example is the thermoflask example. So we have the thermoflask where we have the coffee, or say suppose any hot systems. It can't either it can't either transfer in the mass way or energy way. So that's why we have three different systems, and these are the important systems. Whenever you are doing the experiment, you need to keep it in the mind, or whenever you are doing the thermodynamic problems, you need to understand which one is open system. Okay, whether the question has described as an open system, closed system, or isolated system. So this is the first criteria you need to understand before doing any systems. So yeah, so as of now I have talked in general terms like human body, hot water, thermoflask. So how can we represent this all the terms? As the thermodynamics derives only with the variables. So the main important variables, as we all know that the few of them are pressure, temperature, volume, chemical potential, number of molecules. If I list, there are so many: internal energy, enthalpy, entropy. There are so many properties which are macroscopic, and yeah, we will go. If we go deep diver into the system, you will understand what is pressure and how the pressure, temperature affects the thermodynamic probabilities of system. So once you know the system, and once you know the surroundings, now comes the part, the main course. Sorry, the main part of the course is classical thermodynamics and statistical thermodynamics. So as we all know that in the review class, sir has also been told to us that the classical thermodynamics majorly deals with the macroscopic approach. Statistical thermodynamics basically deals with the microscopic approach. So why we have two different approaches was initially in 1800s, or when the thermodynamics was being built, there is no information about the atoms or molecules. So what they did was they have taken all the entities in the normal microscopic entities, so such that, like say suppose if you have taken, how to say it, if you have, one second, say so, say suppose if you have taken one cylinder with a piston on it and there is some gas molecule. Yeah, so what they did was, so they don't initially they have considered that each molecule as a one sphere, the hot sphere. So that's what they are not, initially they don't have entities about the what is atom, what is a molecule, or what is the electrons, and how the each electron will move with around its velocity. So they don't have much information about it. So they consider every molecule or every gas particle as a hard spheres. So once they consider it as a hard spheres, so there comes the topic of uh, how we call it, number of molecules n. So they just consider how many hard spheres we have, and what is the volume of the system, and what temperature we, what is the desired temperature we will work, and what is the pressure we need to apply. So that's why they initially they carried about the microscopic approach. And once they, okay, once by later on, to understand that how the particles are evolving, there comes the microscopic approach, which we will talk about in the later classes, maybe after week 5 or week 6, where in this case they have taken the consideration of, okay, we already have the microscopic approaches. Say suppose we have the atom, say suppose we have water molecule. Just I am drawing the outline. So it will be O, it will be H. So yeah, you have the water molecule. So in the microscopic approach, they consider it as a single sphere. So but when you come to the microscopic approach, see we have here three atoms, and we have n number of water molecules, and each molecule moves with a certain velocity. To give it in the proper position, each one will have the x, y, z, the positional. These are the positional coordinates. Each atom will have each each atom of the molecule will have the coordinates. Along with that, each molecule will move with a certain velocity, and it will have a certain momentum. So that will be given by the Schrodinger equations. So that's where, if you see that recently there is a abrupt changes in the research field of DFT Gaussian approaches. So that is the, for the next topic we will use the microscopic approaches. So basically the microscopic approaches are mainly used to deal with the study the atoms and molecules. So that's why the course has built in the way that to understand majorly the macroscopic approaches, and then further the microscopic approach. So once we are talking about the macroscopic approach, we need to know what do you mean by extensive properties and what do you mean by intensive properties. So when I'm talking about the extensive and intensive, so as I given you the equation, extensive is the one multiplies by the system scale. Say suppose here we have one cylinder. Once if I increase the cylinder, what are the parameters which will affect the system? Say suppose I have the volume of 5 liter. Okay, just assume that I have the 5 liter volume. Now I am increasing this 5 liter to the 10 liter. So and I increase the number of so if I increase the molecules, sorry, if I increase the volume, so the volume is changing, and I can increase the number of molecules also. And as the if you change the number of molecules and volume in the system, the total internal energy will also change. That's why it is called as extensive properties. The extensive property is nothing but uh, what we are multiplying the system scale. So to come the intensive properties which will remain constant overall. Say suppose the temperature, if I increase it to 5 liter to 10 liter, if I take two different systems or whatever, the temperature of the whole cylinder will be the same and the pressure applying on the system will be the same. On the chemical composition, say suppose if I have the water molecule, the chemical formula will be the 18, okay, atomic weight. So that changes, that will not change throughout the system. So that's why it is called as intensive properties. So uh, can we change any extensive properties to the intensive properties? Because as we are saying that extensive properties changes with the intensive properties, so is it any possible that can we make any extensive properties to the intensive properties? To this we need to understand that, okay, for that, say suppose the volume is extensive property, but molar volume is the intensive property. So what we will do was we will take the total volume. So how we will decide was we will take the total volume divided by the number of molecules. So once you have done it, we will get the specific molar volume. So that's what once you get a specific molar volume, it is the space occupied by that single molecule in the whole volume. So that will always be remains as a constant property. So that again, you can convert the any extensive property intensive property by dividing with the whole number of molecules, such that we will get the specific say suppose specific molar volume or specific number, specific composition, everything. So once you get the better understanding of, okay, we have the system which is the closed system or open system or isolated system, and we define each system with the pressure, temperature, and other extensive or intensive properties. As of now we have understood that, okay, why we are doing classical or why we are doing the statistical. So before and then here comes the thermodynamic laws. So as we all know that there are Newton's laws and there are thermodynamics laws. So you should remember one thing, that the thermodynamics laws is been given without any proof. But as of now, since the thermodynamics laws started in the 1800s, from 1800s to the till 2025, nobody has proven the any law. But the irony is that nobody has proven it has failed. So that's why, like, if you take I think somebody wants to join. 1 second. Yeah. Sorry for the gap. So if you see, nobody has what do you call nobody has proven any thermodynamic laws. So it has given by the scientists at the 1800s, and they said that from till date the laws are not proven by anyone. But if you take any example from these laws, that can be proven saying these things. So to put it in like a story, if I say that the best story which I have heard was. Uh, so basically, the thermodynamics. If I talk about the thermodynamics, it's nothing but a notation of saying thermo is heat. Sorry, for the next class I will make this proper. Thermo is heat, and dynamics is motion. So if you, yeah, so you can understand from these two words that thermodynamics, basically thermodynamics deals with the motion of the heat. So what do you mean by motion of a heat is, so if you take the example of fan, so the fan, we are switching on the fan, and the fan is rotating and it is giving the mechanical energy. So what we are doing was we are converting the electrical energy to the mechanical energy. So what happened here was there is a shift, there is a motion of the heat from, so motion of the heat or work done from one form to the another form. So that's what the thermodynamic laws explains. So if you go through, like, so there are different laws in thermodynamics. So I will give the overview. So there is like zeroth law, first law, second law, and third law. So there are four different thermodynamics laws which deals with different components. So in this, uh, the first week basically deals, the first week of your NPTEL course as deal with the zeroth law, with the temperature, where we will get the outflow of the ideal gases. So from here we will get the story of ideal gas, where we got the story of ideal gas. So to put it in the good words, I will give you one example. How to say it? You have one. You want to sail the ship through the wind. So what does the thermodynamics says was, okay, if we have see, it follows the rules of thermodynamics, saying that okay, we want to convert the wind energy to the to move the particle from one place to another place. So that is applicable for the second energy, first law. And then what does the entropy says? If you have seen the Tenant movie, if you have seen the Tenant Nolan movie, there the movie discuss entirely on the entropy system. So what entropy will do was, say suppose if you have done any work, say suppose now the class has happened from the 15 minutes, we can't take anything as a backwards. Whatever happens, it will go in the forward motion of the time. So it will deals about the forward motion of the time. So basically, if you tell the textbook meaning, the amount of work carried out from the point 1 to point B. So that is the entropy. So to give it in a good example, if you have seen the Tenant movie, there they are talking about the reverse entropy. If you see the movie of Tenant, so what he will tell was, if you fire the bullet, it will go it in this form. But what they will do was, they will take the form of reverse entropy. He will twist the entropy term to the reverse entropy. So basically, in entropy, what will happen was, once the time has been done, say suppose you threw the chalk or you threw the ball, so the motion of the particle has been already begun. So you can't redo the image by doing it in the reverse way. So that is not applicable. So that's what entropy tells. Basically, entropy tells was the motion of disorderness in the system, how the molecule is moving forward throughout the time. And the third law tells about the numerical values of the entropy. Say suppose, okay, we can achieve entropy at only 0th Kelvin. So that is the basic assumption of the third law. We will, as further we will go, we will discuss about each law with respect to the equations. So yeah, so we got the meaning of thermodynamics. So now we'll understand what is equilibrium. So how can you say what is equilibrium? Now my how to say it in the equilibrium. Say suppose I have certain amount of grains in my bag, and I kept it at one position and I left it for some time, and say suppose after 1 hour or 2 hours I came afterwards and there is no changes in the structure or anything, so then I will call it as equilibrium. It basically what says was, irrespective of the time, there should not be any changes in the system. So that's what the lame definition of equilibrium. And the proper textbook definition of equilibrium says that at microscopic level, the system attains a state in the sense, uh, movement of a particle from one form to another form. Say suppose I will explain you the state in much better way in the coming slides. Attains a state where it appears to be static and its microscopic properties remain constant and uniform. uh, See, already we discussed that what is the microscopic properties, the macroscopic properties. So once I kept the grain, say suppose it has 100 grains in it, in the box of volume this much, which is under this temperature, and I kept it as it is in the some cold room, say suppose at the 0 degree Celsius, and I left it for like 2-3 hours, and then I came it back and I rechecked the what is the number of molecules and what is the volume and temperature. If there is how to say it, if the changes in the state is happened uh, correctly, then we can say that okay, the system is in the equilibrium. I will explain that in the further slides. So as of now, we have discussed the how can you define the system and surroundings, and what are the different types of systems we can acknowledge, and how we can say the properties of the system, and what do you mean by classical thermodynamics and statistical thermodynamics, and what are the laws which we are incurring. So basically, the law states that we are dealing with the three terms: temperature, one is temperature term, one is energy, one is entropy. So basically, the thermodynamics deals with the motion of heat. Say suppose uh, if you take any particle, it will have some internal energy which is in the unorganized form. So what does thermodynamics tell was, so we will take one unorganized form of energy and we will convert to the organized form of energy. So that's what we will do was motion of heat. So what we will do was, we will take from say suppose internal energy to do the some work. So this is basically what the thermodynamics does in overall any system if you take. Yeah. And that if you have seen the famous quote also, in energy we can't say that it cannot be created nor destroyed, it can only change the forms. So once we know what is the basic thermodynamic laws, so what we can do was, yeah, so yeah, we have already discussed what is how to say it, open system, closed system, isolated systems. Now we have the example of homogeneous and heterogeneous. So what do you mean by homogeneous system and heterogeneous system? I will give with one example. Uh, how to say it? Mm. Uh, the glass with ice and water, that is one example, and the coffee in a thermo flask. So we have two examples, and you can also say this one, like if you are doing some experiment, you can say that ethyl alcohol in the water, or if you say the different way, oil in the water. So we can take any two examples. Now and human body also. Say suppose, if I go to the example of say thermo flask where we have the only coffee, you can assume that okay, coffee is made of milk, water, and the raw materials and additives. Sorry, everything. But if you see it, it has only one form. At the end, it has become as a coffee and it stays in only one form. So that's why it is called as homogeneous. Even though it is made of, as we are discussing about the microscopic properties, we will not focus on that. Okay, what are the properties of the milk? What are the properties of the water? What are the properties of additives you have added? What is the grain molecule size? What are the atoms you have taken for the coffee powder? See, these all are the microscopic approach. So, but when we are talking about the classical thermodynamics, which we focus on the microscopic, we will consider the phase of in which the solute, which in which the given system stays. So basically, if I say that okay, coffee in thermo flask is basically the example of homogeneous as it has only uniform phase. So that's what the example gives. That's what the definition says, that a system consists of a single uniform phase, as given in the coffee example, it is in the liquid phase, where physical structure and chemical composition are consistent. So now, once you mix all the things, the chemical composition will be in the consistent form. So, but if you take the heterogeneous, it says the system consists of two or more distinct phases. Say suppose ice in the water. You can say that the ice and water both are same, but they both are in the different formats. So that's what we can differentiate, that okay, what is homogeneous and heterogeneous. You need to make sure that okay, whether we are taking isolated system or closed system or open system. Once you have make sure that okay, these are the important systems, and then you need to understand whether it is in the homogeneous form or heterogeneous form. To understand that say suppose I can give you example of that. Thermoflask is the example of isolated system but homogeneous system. If I take the water, it is like a say suppose glass of ice and water in a open lid. What it will give us, it is converting the, see, the mass is not distributing, it is changing the energy from one position to another position. It is transferring the mass. So that will be example of a closed system but heterogeneous property. Okay, so you need to be sure that whenever you are coming through the thermodynamics problems, you need to understand that okay, what can be the system first, and if you know the system, and you need to understand that which system, which type of system, whether it is homogeneous or heterogeneous, that will be depend upon the how many distinct phases you have. So yeah, as I said that different types of examples of homogeneous systems are coffee in a thermos, mocktails, gas mixtures. Because in the dry air, if you see that which we can't able to see, all the molecules are having the same size. Like suppose nitrogen, oxygen, everything in the outer space will look like same. So that's why it is all, they are distinct, but they are all having the same chemical composition. So the uniform phase. So that's why we call them as homogeneous. Once we come to the heterogeneous, we have the glass of water and ice, human body, where we have the different types of chemical reactions happening in our body. Not only chemical reactions, say suppose we have different properties in our this and the mixture of water and oil. So here also we can say that they both are in the liquid phase, but there forms the different phases between water and oil and boiling water. Say see, boiling water also again comes in the system of open what you call open system, where you are boiling water and it is converting from liquid to the gases. So where it is converting its mass and energy, at the same time it is heterogeneous also. So you need to be clearly understand what is heterogeneous and what is homogeneous, and then which type of system it falls into. So and one more important topic in this was state variables and path variables. Say I will give best example. Consider we have one system of gas molecule moving from one equilibrium state to another equilibrium state. Say that I have 5 moles of hydrogen. Say 5 moles of hydrogen in the, say this is the container with 5 bar and 100 degrees Celsius. It is moved to, so the volume is constant here, so don't think that volume is changing. It is moved to 1 bar and sorry, it is moved to 50 degrees. So both are in the equilibrium state. So here you need to understand in thermodynamics, the equal symbol gives that you may think that the pressure and the pressure and temperature values are different, so the both system will be different. No, what basically we are saying that the both systems are in equilibrium at different places. So initially it is at the 5 bar and 100 degrees Celsius. As it moved to 1 bar and 50 degrees Celsius, that's it. The both are in the equilibrium state. So now how can you define the state variable and path variable? So if I plot that the both systems, say here you can see there is a one system, and here you can see there is another system. So these are the state variables. So state variable, what does it says was, we are focusing on only on the end point and the starting point. I know what is the starting point. Sorry, yeah, I know what is the starting point and how it is transferred to the this point. So only this is the important information for the state variable. So we will calculate the what is the energy work or whatever the work has been done from the outer path to, say, from the initial point to the final point. So we will only focus on the 2 points. So to be put it in the good example, as given in the our tutorial weekly lecture also, we have two different distinct points. Say suppose you are at the down of the peak and you are on the top of the peak. So what you will do was, if you take only this one, say suppose this is at the height of 100 and this is at the height of 50, what you will do was, you will take the difference in these two and you will make it to as a 50. So this is directly state variable. So what you will do was, you are taking the final one and the initial and final and done. You have calculated the what is the difference in the height. So there is another way, which is the path variable way. So if you see it here, there is a path variable way. It is also same thing. We have the initial, we have the final, but here to reach from the initial to the final, there are n number of ways. I have shown here 4 different ways. So what I want to conclude from this point of view was, say suppose that it may take this path, say suppose this path, or it may take this path, if you see clearly, or it may take this path, or it may take the straight path. So what does the path variable explain us much better than the state variable was? Say suppose in the state variables, if you take the state function as a equilibrium state, it will only focus on the 2 points. Okay, I have the initial point and final point, and it will calculate it. But if you go through the path function, it will tell us that which path it has followed. Say suppose, so we I think you might have heard about the adiabatic, isobaric and isothermal. So sorry, if I take it from this point, from the initial, say suppose this is the initial and this is the final. So if the molecule, if the system has moved this way, say suppose initially it was in the 100 and slowly it came to the 50 from 5 bar to 1 bar. So here if you see, it is a constant pressure. So if once it is a constant pressure, it is isobaric. So then it follows the isothermal process. You can see it, right, the difference in the isobaric to the isothermal. And if you see the green line, it is initially it is following the isothermal and followed by isobaric. And there is a pink line which is adiabatic, which says that there is no heat transfer between the systems. So the path function tells us that, okay, what will be the energy losses and how can we gain it. So this is the basic difference between the state functions and path functions. So basically state functions, what you need to remember was, state function deals with the final point and initial point. Say suppose if I give any equation, say suppose Na plus Cl gives rise to NaCl. If you take this equation, this direct function is, if you take the state function as one of the example, okay, if I ask you to make Na plus Cl gives rise to NaCl, and if I ask to make the delta G out of this equation, so there are two different ways to make the delta G out of this equation. So one of the way is, okay, I have taken Na, sorry, one second, plus I'm just making it, so suppose Cl gives rise to NaCl. So what it happened was, if you take the state example, state pathway, state function, what it will tell was, okay, I have the final, I have the initial values, and what it will do was delta G equal to this minus this one, forward minus backward reaction. But the same thing, if you take the path variables, what will happen was, this equation will be transferred to the several multiple small steps, like Na plus of Cl gives rise to Na of Cl, then NaCl minus, then we'll add, like, see, we'll have 2Na and 2Cl, then only we can add the two compounds, because to get the neutralized system. So it will have the radical formation, and then from the radical formation it will form the equilibrium position. So at least it will have the 5 different steps from the Na plus Cl to the NaCl. So in that way, it goes from Na plus Cl to the NaCl through Na of Cl, then NaCl minus, and then it takes the radical formation, and then NaCl. So the path will give you the preferable path which he has taken it. So you should be remembered that whether they have taken the path function or state function. If you ask me, will the values will be different from the state function to path function? No, mostly the values will be the same. If you take the root of path function, or if you take the root of state function. So yeah, so now until now we have discussed the topics of the basic topics, like what is system and how does surroundings affect the system, and we have the boundary. So I think didn't talk much about the boundary. I will explain later. I think I can explain it now also. So basically, so first I'll give the quick review of what we have studied like last half an hour. So we have system, we have the surroundings, we know what is the system, how to define the system, like open, closed, or thermo isolated. Once we know, then we know which is homogeneous or heterogeneous, and then we know, okay, if it is homogeneous or heterogeneous, how can we know the properties of the state? By giving the example of microscopic properties, and we studied that what is macroscopic and what is microscopic, and which are the thermodynamics used to study the both. And then I think we have studied the extensive and intensive properties and the state functions and path functions. So as I already discussed that zeroth law is the one which I discussed with the temperature. So say suppose this is the one best example which I can give. Say suppose there is there is a one particle which is very, say there is one box which is very hot, and there is one another box which is very cold. So you all know that if you bring together the hot one and cold one, there will be a warm temperature. So what happened here was, when the hot surface interacts with the cold surface will interact with the hot surface to get warm. Okay, so that's what happened here. So that's why representation, the color changes the form. So this is the basic law of thermodynamics. You can understand, you can think silly that okay, why the law is made upon this. It is basically says that when hot water sorry yeah when hot water is mixed with the cold water, you can assume this thing anywhere. When hot water is mixed with the cold water has become the warm, not the hot water. You should remember it in this way. So there is another example. A gives rise to B. See, again, these are the three different systems: A to B, B to C, and C to A. And the basic, sorry, it should be C. I think there is a mistake. Yeah, it is C. So the first assumption is, sorry, somebody is joining the call. I think, 1 second. Let me admit him. I think, sorry. Okay. So yeah. Uh, So what is happening was, say suppose if the temperature of A equal to B, say suppose here the temperature is 300 Kelvin, if the B is also 300 Kelvin, and if the C is also 300 Kelvin, then it should be like A to C. I have another question. Can you just tell me that how the temperature flows? Say suppose, as I given in the first case, the temperature goes from hot to the cold, not from the cold to the hot. Okay, hot body will make the cold body as a warm body. With that example, can you give me that how the temperature flows if A is a hot body? So this one is so this is a hot body, and this is warm body, and this is cold body. So can you just understand by yourself that how the heat will be formed? Heat will be transferred between the systems. Like as I given the example of A to B, hot will be given the temperature to cold to become the warmer. So in the same way, can you explain me that? So basically, what we'll think was, okay, A will give to B, B will give to C, C will give to A. So this is the basic understanding of what basically what we'll think. Okay, we have three different systems, and okay, what if A is the hottest body and B is the warm body and C is the cold body? So can you guys tell me how does the temperature flows from hotter body to colder body? if we can understand, basically it flows through this way. It will go from A to B, A to C, and B to C, not C to A, because C is a coldest body, and it will not even go from C to B. It will only go from A to B, A to C, and B to C. Okay, I think you got this point what I'm saying. So okay, so now you understand that, okay, what is the zeroth law says. So where does the zeroth law applicable? You can see that, okay, I have the temperatures. Sorry, you have the temperatures, say suppose A and B, C, you have the three different systems and you have the three different temperatures. Okay, I measured it and I figured out it. So what is the use of this? So where can I actually implement the zeroth law? So that becomes the temperature scales. So what we call as the thermometer. Say suppose the temperature in, you can say that, if you see the weather app, you will see the temperatures, right? You can, if you have any Android phone, you can say that, okay, what is the temperature in Patna, and what is the temperature in Delhi, what is the temperature in Hyderabad. So these three are shown. See, just assume that A, B, C, these are the three different positions. I just given as example. So I have A position, say suppose this is Patna, and this is Delhi, and this is Hyderabad. Sorry. Okay. So now what I have done was, okay, I have taken one instrument which is called as X, and I went to the Patna, I measured the temperature, and I came back and I went to the Delhi, I measured the temperature of Delhi, and then I came back again to the Hyderabad, I measured the temperatures and I given it. So there should be some reference points, right? So as we know that there is 0 degrees and 100 degrees Celsius, -10, -20, or -273 Kelvin. But what is the, so this all arises from the zeroth law of thermodynamics, where we says that, basically thermodynamics law, okay, and one more thing was, say suppose here it is in the red color, if you see it is in the blue, it is in the yellow. So what does it says was, say suppose if you take the metal body which is in the if you heat it to the certain extent, much more than its boiling point, it will turn to the red color, and once you make that red color into dip into the water, the red color has been converted its color from red to the black. What does it says was, so we are understanding the heat transfer through the norms of color change here. So basically we can understand the transfer of the heat in any form. So like suppose there is a resistivity where it can transfer the electrons from one form to another form, or it can change the color. So based upon this, in the late 80s, sorry, in the late 1800s, uh, yeah, so as I said that the zeroth law has been used as a temperature scale, and the most well-known scales are Celsius, Fahrenheit, and Kelvin. So basically, what they have done was, they have taken, as I said before, here if you see that, in this case we have used the color example. In the same way, in the 1800s they have taken mercury as one molecule, and they have taken the boiling point of water and the freezing point of water. Say suppose the boiling point of water is 100 degrees Celsius, and the freezing point of water is 0 degrees Celsius, and they have taken these two as a reference points, and they have taken the height raised by the mercury level is the, what do you call, temperature given by that system. So that's how they design the temperature scales. So yeah, to identify the temperature difference, they use a different techniques. Some use mercury, some use resistivity, some use color change. So we can't use the mercury in the case of silver staining. And if you can say that, for humans you can use the mercury, that is the oldest form. And some use the resistivity, like where the electrons are transferred from one form to the another form. Yeah. So now, till now we talked about the how the temperature is been implication on the world applications. Now comes the ideal gas theorem. So what does the ideal gas theorem was? So initially Celsius has given that, okay, we have the two freezing points, one is 0 degrees and one is 100 degrees of Celsius. By taking this, Fahrenheit has developed it further, saying that, okay, the human body will consist of 98.6 degrees as a normal temperature, but they all are missing the some major thing was, okay, what if, and they said that, okay, the another thing was, a boiling point of water is 100 degrees Celsius, it is at what pressure and what volume. So nobody has mentioned reciprocal, what do you call it, usage of the boiling point as standard term. So for there it comes the Boyle's theorem, which says that I have taken the two microscopic properties, which is pressure and volume Okay, you can see it is a specific molar volume where it is a constant intensive property, and then we have taken the pressure, which is again the intensive properties. We have taken two intensive properties. Say suppose I have taken the one volume and one pressure, and I mix it both, and then I take another value, then I take another value until I reach the zeroth value, and it is all going to the constant, which is in the function of uh, time t temperature. So this is the temperature. So this is the temperature. So what the from Boyle's theorem, what they have done was, so if you see that from Boyle's theorem, okay, they have taken the initial 0 point, and then they have taken the 100 as the temperature. So what they have taken was, they have taken two systems. Say suppose they have taken a random, I think, yeah, they have taken random gas, and they have taken at the 0 degree Celsius. Okay, and they have taken at the 0 degree Celsius, and they have taken the some pressure and volume of that particular gas, and they found there is a 1 point. And what they have done the further was, they have taken 100 degrees Celsius, and the same thing they have done. So now they have 2 points, and they want to see, they want to come to the correlate to all of systems. See, they can't able to do every time, right? So they can't able to take two systems and do at different multiple times. So what they did was, okay, they plotted this graph, and they try with the linear interpolation. Because if you take any quadratic, say suppose if I plot the quadratic between these 2 points, it will go like this. Sorry, the graph is not, if it is hmm, 1 second, yeah. So if I make, yeah, if I make the quadratic will go like this. So the quadratic will never reach the zero. As it goes the negative value, it will goes to the minus infinity. So that's why they didn't take any quadratic. So what the researchers was done was, they have done the linear interpolation. So what does it do was, so they have taken 2 points, and they made the axis through that, and they found out that, okay, it is not the stopping point. So where does the temperature as reaches the minimum? So that is at the minus 273 Kelvin. So if you see, minus 273 degrees Celsius, minus 273.15. So this is the point where the temperature has, where the limit tends to PV is become the constant value at the given temperature. So that's what they said that, okay, the Celsius has given that for any gas we can take the reference point as a 0 and 100 degrees Celsius. But when the Boyle's theorem has been conducted, they found out that, okay, we can't take 0 degrees as a reference point for any of water. So what they have done was, okay, they have from here the Kelvin has made the new points, which says that time of t plus 273.15. So this is the new reference, this is the new temperature scale they have given by the Kelvin, saying that, okay, as we have done the calculations, and we found out that the minimum temperature is not the 0 degree Celsius. So that's the reason we need to give the higher temperature. So that's what they introduced the Kelvin scale. Okay, now I have taken the Kelvin scale, okay, and I say that, okay, this is the temperature. If you see, yeah, thus the new Kelvin scale with reference point does not hold true for water in all regions. So what do you mean by does not hold true for all regions? Was, say suppose sometimes the boiling point of water in Norway or in some other foreign countries, it will be like 80 degrees Celsius or say 120 degrees Celsius. It is not constant for every gas and for everywhere. To be in the system says that, okay, 100 degrees Celsius will be the proper way. So to overcome this limitation, the triple point of water has come. So what do you mean by triple point of water? I think you all know it. So it is the temperature, and what does it do was, so it will go like this, if I'm not wrong, yeah. So sorry, it will go like this. 1 second, yeah. So I'm just drawing the rough drawing. So we'll have the 3 points. 1 second, yeah. So what we'll have was, we'll have 3 points. Beyond that, so suppose this is solid, this is liquid, and this is gases. So this point is known as the triple point, which, so they have given the reference point, initial reference point, following this formula. If you see, this is the initial reference point, and later on they have taken this triple point, says that, okay, this is the new reference point, which is 273.16 Kelvin. So if you can see that in the sea, that's what written here. The triple point of water is the point where water exists in liquid phase, solid phase, and gaseous phase. So what they have done was, Okay, see, as the people says that at 100 degrees Celsius, maybe in India it is a boiling point. In maybe in some countries it is still in the liquid form. Maybe in some countries it might be in another form. So what they done was they have taken that. Okay, what will be the point of junction where the water will be in the liquid phase, solid phase, and gaseous phase, and that point has been made into the point that which is known as the triple point. The triple point is at the position of 273.1 Kelvin, sorry, 273.16 Kelvin, with the pressure of 611.73 Pascal. It is nothing but basically, if you see, it is none other than it is 0.01 degree Celsius, if you see it correctly, and it is 6.11 into 10 to the power minus 3 2 bar. So yeah, so what is the use of triple point? So once we got the triple point, from the triple point, okay, we got the ideal gas theorem says that we have, if you see this function here, we have the limit tends to PV, which gives the constant and f of t. I think okay, and from this that equation, assume that limit tends to PV is y equals to mx form, and you are getting f of t into t, because on the x-axis we have the, here you can see this is the x-axis and this is the y-axis. So if I make the slope of this particular line, if I make this, I think I can change the color of this diagram. Yes. Yes. Sorry. Yeah. If I make plot with the temperature T with f of t, which goes like the straight line interpolation, it is the zeroth Kelvin, which is minus 273 degrees Celsius, and this will be the triple point of water. So if I'm sorry, triple point of water. So what does it says was, if I take the slope of this line, it will be like, so basically that is the one which is given by the limit formula, limit P of V bar equal to, this is y, which is nothing but in your case it is f of t, is equal to, the slope of this line is m is nothing but f of t by t at that particular position, f of t by t into t. So this is the equation which we have. So this is basically limit p tends to v. F of t is nothing but limit p tends to v, and this is the constant value, and this is the temperature, which is x term. I think you are getting this point. So from this, what we will done was, so we made this as a PV bar equals to, so this constant I made as a r term, and there is the temperature. So this is how the ideal gas has been developed. So if you can see that there is a formula, I think it's become the clumsy. 1 second. Yeah. So I think you most guys understand that how the PV equal to RT came. So basically it came from the temperature scale. Okay. And so suppose here we have the three different intensive properties. One is pressure, volume, and the temperature. So from that we get the equation of state, saying that okay, I don't need to know all the properties. Say suppose if I know how many number of molecules are there and what is the pressure and what is the temperature of the system, I will know the volume. If I know the volume, if I know the pressure, if I know the number of molecules, I will know the temperature. So this is how, so this is how you will find the thermodynamic state of the thermodynamic state is nothing but that at that equilibrium state what are the properties that it possesses. So that we can calculate through using the ideal gas theorem. Okay, once, okay, as of now I said for the ideal gas. So you should remember that ideal gas works for only low temperatures and low pressures, because we are given that the temperature of the ideal gas will be in the range of minus 273 to 0. If you say it works for only low temperature. But if you make any, so if you are from the chemical engineering, if you make not only chemical engineering, if you make any plants, or if you want to make any synthesis design, or if you want to make any bioreactors, not the bioreactors, suppose if you want to make any boiler where the temperature of the system will be much more higher, and if you take that cases, the ideal gas will be collapsed. The ideal gas will be collapsed entirely. So what you can do was, so for that There are different forms to expand for the real gases. So ideal gas is PV equal to RT, which is PV equal to nRT, because if you, this is nothing but, sorry, I will give you one more way. P, the specific molar volume is PV by N, it is equal to RT, which further gives rise to PV equal to N R T. I think this is clear. So PV bar, it is a specific molar volume which is divided volume number by, as because it is become the intensive property. Now we have the two intensive properties, one extensive property. Now the volume is changing, so it has become the extensive property. So now, so this is how we got the ideal gas equation, and this ideal gas equation works at low temperature, because this ideal gas theorem, this ideal gases equation has been developed from the ideal gas theorem, which works at low temperature. So if you can see that the triple point temperature is 273.1 Kelvin, which is if you convert it to Celsius, it is around like 0 degree Celsius, and it works in the range of, how to say it, for the smaller scale. So what if the scale is very big? What if we take in the real gases where it has higher temperatures? So for that, there are the researchers has developed many formulas to derive the equation of state. So basically, the equation of state we need to find out, because we need to know what is the system's volume, temperature, pressure. If you don't know one thing, because we need to understand that, okay, if I am applying in the later part, you will understand that internal energy terms and all the terms. From there, we can understand what is the use of equation state. For as of now, we can remember that to understand any macroscopic properties or changes in the system, we need to know the equation of state. To design this for real gases, what will be the equation? So for the ideal gas, it will be PV equal to nRT, where if you know any two particles, we will get to know about the remaining one. For the real gases, the major formula is given by van der Waal. I think you might have seen this formula. P plus, sorry, yeah. So I think let me put it in a good way. Yeah, I think you have seen this formula in your books or anywhere. P plus A by V square into V bar minus B. So I just want to give one outer space of this example meaning, like, so that you don't need to mug up or anything. You don't need to remember it like, okay, you need to remember this formula. No. So basically, this equation comes from PV bar equal to RT. So this is the basic equation which we have. Now, okay, just assume that one second. Yeah, just assume that this is the system which we have, and once you have the system, uh, okay, we are talking about the V bar. V bar is nothing but the entity of the whole molecules. Okay, suppose now entity of the whole molecule. So, but but we have the small molecules which are covering this certain space in the whole volume. So when we are calculating for the real gases, we need to understand that what is the remaining space. Okay, so that's what here the B is the nothing but the space occupied. So here B is nothing but the space. Sorry, yeah, here B is nothing but the space occupied by the individual molecules. Say suppose that's what V bar is the total volume, but in here the total volume is not the total volume, because there is some atoms which are constituting some space. So that's what we are removing that particular space from this equation. So that's why V bar has become V bar minus B. It is nothing but a new V bar. It is, sorry, it's not under division. It is nothing but a V bar. So what does it says was, okay, initially we have the whole specific volume, but now, okay, we want to understand that what is the free volume space. So how can we get the free volume space? Was we will delete the number of we will delete the space occupied by the atoms. So that's why the V bar has been given as V minus B. And the second thing was, in the macroscopic properties, what they have done was, say suppose if this is the molecule, as we all know that each atom will go and hit the surface, it will collide here, and then it will go back, and then it will go back here, and here there is another molecule which will have the attractive force towards it, and we have another molecule which will have attractive force. So what does attractive force says was, it will ask, it will pull the molecule towards it in such a way that it will not go on, what do you call, not go and collide with the systems, and sometimes it will have the repulsive forces also. So okay, so basically if you say the, okay, just assume that to put it in the bigger circle, I will put it like this. You have a box and you have the piston, and okay, you are applying some pressure on it, and there are some certain molecules. So okay, certain you can say certain molecules are there, and each molecule is moving in its own arbitrary space, and it is trying to collide with it. So when you apply the pressure, so basically this equation says that this is the pressure and this is the volume. We know why the volume is divided. So at the pressure, we assume that the pressure is only, it's not the outside pressure which we are applying, it's not the only external pressure. What is happening was, along with the external pressure inside, what is happening was, this molecule is sorry, one second, I will put it in the good way. Yeah, this molecule is colliding with this surface, and this molecule is trying to stop this molecule by having its attraction power, or say the repulsive power. So there is some, might be there is a repulsive when the two molecules come very far together, you know this statement, right? So if you go further, you will understand this one. So what does it say? Was this is the radius. Say suppose as the distance goes nearer between the two atoms, so here the distance between two atoms is very large. So as you come bigger, there will be more energy, and if you come together, say suppose this is one molecule 1 and this is molecule 2. If you go, if you go nearer to the system, there will be certain point where there will be much more attractive force. After that point, there will be repulsive force. You can see that there is a lone pair of electrons which will repel each other, and it will move the space from this side. So this is also creating some external internal pressure on the system. So to add whole pressure, what we are adding was, okay, we are taking the pressure which we are applying on the system, which is this one, followed by we are taking a by v square. A is the nothing but the pressure acting on this one, divided by v by square. What v by square was, okay, what we are taking was, okay, what is the space in which, say suppose this is the molecule which will have its range, so van der Waals range. How many molecules are there in this range? Suppose if the molecule is near to here, or say suppose somewhere here, we will try to understand that, okay, which is the molecule which we have, and what is the distances it can have. Say suppose here, suppose if you take in general example, the distance between this atom and this atom is very far, such that there won't be any interaction forces. So basically this value will become 0. So that time it will be the only PV minus RT. So because in ideal gases also, what we will do was, we will increase the volume in such a way that each molecule will become very small. So suppose we know that this is the, say suppose this is the open area where we have the nitrogen, we have the different types of argon gases. If the volume is less, this will be nearer to each other, okay. And then comes the real gas equation. So real gas, okay, if the two are nearer, they will be collided and there will be more increase of energy. But if you increase the volume in such a way that there will be far distances, and such that the molecules will never know that, okay, this is also existing because of its repulsive forces, that's why this value becomes 0 in that case, okay. So and that time, so the space here, say suppose uh, if I use the real gas equation for the ideal gas, so this is the ideal gas where the volume is in infinity, and the space occupied by the each molecule will be very far low, such that it will become 0, and there is no interactive, and there is no two molecules will be in the same van der Waals interaction zone. So this will also become 0. So again it will go to the equation of PV equal to nRT. I think, hope you all get that, how to go from van der Waals to the, how the van der Waals has designed the equation from ideal gas to van der Waals. Van der Waals is nothing but when you have the smaller space with higher temperatures, we'll play with this, because you need to remember that ideal gas is applied for only low temperatures, because it comes from the triple point of water and the minus 273 degrees Celsius, as they both act as the reference points. So these are the things. So this is basically the van der Waals forces. So once we got to know the van der Waals forces and everything, and now so yeah, so we are now until now we have understood that, okay, what is the effect of temperature on the gases, what is the effect of temperature on how can we measure the temperature, and how the zeroth law tells. So basically this is the thing which was happened in the week 1. And okay, initially in the starting of the class I said that thermodynamics is referred to as converting the disorganized form of energy to an organized form of energy. And once okay, I said that, okay, in 1800 some scientists said that, okay, the we will keep one name as thermodynamics, where it will transfer the disorganized form of energy to the organized form. But there is no such proofs saying that okay, how can it do. But it's all based upon the large number of experimental observations. Say suppose I will convert, as I said that first law of thermodynamics deals with the energy, where we says that energy can neither be created nor destroyed. If you take that example, based upon this the conversion of energies, they have taken they have done the experiments on n number of experiments. Like suppose the Boyles did the experiment. I think in the next class you will learn about the Joule's law. In the week 2 I think Joule's law. So where they have done was they have taken the enormous number of molecules and they have done the experimental observations, and they figured out okay, we can't prove it. At the same time we have the certain proof saying that this all are correct. Okay, that's what that's how the and once we have four laws. Okay, and we have the equation set, right? Say suppose for ideal gas it is far easy to design that okay, we have V equal to f of npt. If you see, for ideal gas it is very easy to say that okay, this is the equation. For real gases, okay, this is the equation. As of now we have taken the terms of only vpt. Okay, so we have taken the terms of only vpt. So if I have v p t, we know how to express the equation of gaseous. Say either you can use the ideal gaseous condition if it is at the low temperature. If it is the real gases, you can use the van der Waals equation. What if we need to do the thermodynamics with more states? Say suppose internal energy, internal energy, entropy, and what you say, the temperature. So suppose I want to take these three parts as a one system and I want to figure out the thermodynamic state. Okay, in some cases instead of giving volume we will have the internal energy. So you need to convert, you need to understand that okay, how much work has been done through the internal energy. So that time the four laws which will given as not in the case, as it's simple. Okay, I given you the packet of rice. Now if your just interest is to make the normal rice, you just need to boil it. So it is an example of vpt. But say suppose I need to make the biryani. For to make the biryani you need to add the certain ratios of basmati rice, this rice, normal grains, normal rice, and then you need to make it by addition of additional layers and addition of some coriander leaves and everything. So that it's like you have the same system, but if you want to explain the system in different formats to better understanding of the conversion of energy from one form to another, we need to form the new postulates. Postulates is nothing but it's like a theorems. We are stating a statement and then we are following through the statement to make, basically it's like a if you see if you know about the constitution, we have the rules. Okay, we have the laws which says that 1960 to 19 there is amendment acts and there is a orders. Orders are the one which was made, and to make the rectifications in the orders they will make the amendment acts. In the same way here also the laws are, we have the core laws are only these four. We will add the few postulates, we will add the new postulates such that we will try to address the thermodynamic system in much better equation of states. So in the same way that we have three different things which is enthalpy defined by u, h, which the with the example of u plus pv, and Helmholtz free energy which is A equal to U minus Ts, Gibbs free energy G equal to H minus Ts. Basically this has also no proofs, this is also given as a postulates, and they have we will understand that how the internal energy, how the work carried out to be changed to the internal energy, and then vice versa everything we can be carried out. So as of now I have completed with the theoretical part of the week 1 to explain it in the say, because I figured out that okay, it will be better to understand that what will be the zeroth law, from where how we can bring the zeroth law to the system from the ideal gas, and then we have the real gases. Okay, why we need to use the internal energy. So if we have only volume, pressure and temperature, then also we can use the equation of state as it is. But in some problems the problems will deal with the entropy. It's like the amount of work. So basically the entropy is nothing but the amount of work done from by the system to move from one place to another place. So that's what entropy, right? As I said, it is the disorderliness of the system. So if we are talking about the more advanced topics, it's like more advanced what you call as if you want to talk a solution deep diver, we need to have the new parameters. If you have the basic parameters, we will go with the equation of basic equation. But once the what do you call the parameters are changing, we need to change the thermodynamic equation of states. So that's why we need to have the new postulates, and we need to have the new potentials such as enthalpy, Helmholtz free energy, Gibbs free energy, and from here we will get the Euler relation. In the next week we will discuss about the Euler relation, Gibbs Duhem equation, and all the things. So yeah, this will be act as a first week one out course. So if you have any doubts, you can ask me. Then we will go to the how to. I have some few examples we will solve. If you have any questions, I think everybody is, yeah. If you have any questions, you can ask me. Uh, if you understand, if you have any basic questions about the theoretical concept, you can ask me that. Then we will discuss about the how to solve the problems. I think, let me know that if you have if you have any questions regarding the topic, the outline of the basic courses. In the next week we will discuss about the Maxwell equation and all the things. So as of now, if you have any questions about the zeroth law, how the temperature thing, or how the ideal gas equation is formed, or how the van der Waal is used, van der Waal has generated the real gas equation, or if you want about the extensive properties, intensive properties, or how to remember the system. If you have any questions regarding this, you can ask, then we will discuss about it. I'll give you 2 minutes. If you have any
So
doubts.
can you explain the Van der Waals equation again?
Okay, fine. 1 second. Say so. 1 second. So you can see this. 1 second. Sorry. Yeah. I think it can't be done. Mm. So. So you understand the equation, right? So you understand the ideal equation, right? So we have the ideal equation of PV equal to nRT. Yeah.
Yes, sir.
Yeah. So 1 second. I will make one. Give me 1 minute. I will make the new. Okay. Sorry. Keep. I will make the new slide here. Yes. Mm. So yes. So we have that PV equal to nRT, right? So this is the basic ideal gas equation. So what this ideal gas equation do was, we will take a large container. So assume this is a large infinity container, where assume it has a universe where we have the molecules everywhere. So suppose these are the 3 molecules or 4. For the example, in this big box, so here the volume is, say suppose the volume is, say suppose 1000 liter, something like this, and the space occupied by this one. Okay, it says about these are the small molecules, right? So each molecule, each molecule will assume that has taken the space of 0.001. Okay, and as the molecules are very far, there won't be any interaction between these two. Okay, so that time we will use the ideal gas. What if the box is small, I mean the volume is in the finite element and the temperature of this system is high? So that time we need, so if you take these 4 examples, so I will keep like this. So I will draw this one into very small. Okay, yeah. So here there is 1, 2, 3, 4, yeah, 4. So now the entire, sorry, yeah, now the entire volume will be, say suppose x, and now you can't eliminate the volume of the things covered by this atom. So that's why we need to have one statement saying that, okay, this is the V bar minus B. B is the term to define the volumes occupied by these molecules. So here also see, if I go for the microscopic approach, which is in the statistical thermodynamics, there again we need to understand that this each atom will move. Okay, this atom will move here, this atom will move here, this atom will move here. Okay, but as each atom, say suppose this is atom, it will have the xyz coordinates at every single point, like in the time frame it will move with xyz with momentum. Okay, but as we are calculating this particular points in the microscopic approach, we are considering this as a hard spheres. So what we have done was, we have taken 4 as a single sphere, which will be there in the system, and we are taking that, okay, how much volume it will be occupied, and we are minusing that volume, okay, to get the specific volume. And then for the pressure term, so you say suppose this is the container and you are applying external pressure, okay, this is the total pressure. Basically the total pressure is nothing but the external pressure which you are applying. So suppose here you are applying some pressure, and what I am doing was, say suppose assume that this is the same box as this, I just expanded it. So there are so there is one molecule here, and there is another molecule here, and there is another molecule here, and there is another molecule. So we all know that this molecule will collide with this surface, and this molecule will may have the attraction with this one will may have the repulsion force with this, and this one will have nothing to do with this. So what they have done was, you know that if you make the plot of the distance, suppose this is the molecule x, here the molecule x is there, and this is the distance, and this is the molecule y, and as I come together from the molecule x and y, at certain point there will be a higher attraction, and once the point is reached, it will go to the higher repulsion. Okay, I think, yeah, one second. So basically the graph will look like this. So yeah, the graph will look like, so it's like this is the value of basically this value shows the energy, how much energy you need to break the two systems, like to remove the system. So if you go here at initially, if the molecules are very far, you don't need any energy to break the molecule, so that's why the energy almost will be zero. If you see, it is near to the zero. But at certain point, after certain point, if you come to one extent, the both will have the attraction forces, and after a certain point coming very close to each other, where it has the positive electron field against each other, it will have the repulsive forces started, okay. So we need to understand that, okay, what are the molecules. So suppose here there is one molecule, here there is another one. Suppose this is going to collide with this and lose some energy. Here it is trying to attract this, to have the attraction bond such that it won't go and collide with that, it will have the attraction force with this. So due to this, the collision and the attraction force and the repulsion forces, there is some energy, some pressure is generating inside the cylinder vessel. So for that, they have defined the A by V square. A is the what is the pressure developed by this in this particular volume. So V square is like, say suppose if I say 1 by V square is a very say suppose there are two molecules here, one and the second one. As I said that van der Waals force will have a certain extent such that you will have the effect of repulsion or attraction. After, say suppose, yeah, if you take this area, there is no there is nothing to do, because you can see that the values of the distance between x and y is increasing. Say suppose if the volume is the radius of this point, the x and y is greater than, example I'm giving, say 0.02 angstrom, there won't be any effect between these two liquids, so these two molecules. So that's why the volume, whatever the volume, it won't have any effect. The pressure will not have any much effect on this particular uh, atom. So that's why then that time it will become to zero. But if they are very nearer, say suppose if the topic which we are talking about are there in this region or in this region, then we need to consider as the 1 by v square. You can see the electrostatic force also, it will be divided by, if you see, you know, electrostatic forces q1 q2 divided by r2 square r square. So basically what we are doing was, we are doing for the very smaller zone, so that's why we are adding the pressure term developed at that smaller zone. If the zone is very big, say suppose the two molecules are very far, there won't be any interaction or repulsion forces between these two, so that time it will be zero. So it will be basically like a p. And if the volume is entirely big, like say assume that it is infinite volume, where the two molecules are very far interaction and there is nothing to do worry about it. So if you take this condition, 1000 minus 0.001 is nothing but 1000 only. If you put it in the good words, so that time it will again goes to the PV equal to NRT. So this is how this equation is converted to P by A by V square by VB V bar minus B equals to RT. So this, you know, right, this RT comes from the Kelvin's Boyle's theorem. So this is the equation. I think, is it clear?
Yes, sir.
Okay, thank you. You have any more questions you can ask? Then we will go to the how to solve the problems. I think in your week one I saying that there are 10 I think 7 to 8 questions. I have some basic few questions which you can understand. Okay, so I'll give some time. Just read the question and understand the what the question says. Then uh, pick one option. We will decide. Okay, if you know the answer, just let me know. Then we will decide whether the answer is right or wrong. Just take 2 minutes of time to understand that, okay, whether it is whether you understand the question or not. See, we have talked about the intensive properties, extensive properties, anything, but the question forms in different way. Like here there comes a batch process where they are inoculating a system, and then uh, they are collecting the samples to see whether the growth has been done. So in this example, how the thermodynamics is working. So if you see this example, let me know if you know the answer. You can see the question, right? Hello, hello. Voice is hello, hello. I think I'm audible or not. Hello. Yeah, I think so. Yes. Yeah, I think am I audible? Hello.
Yes, yes.
Yeah. Thank you. So can you please answer this question so that it will be better for you to understand, because there is similar questions in the assignment also. So it will give the correct idea of what is intensive properties and extensive properties. So have you read the question?
Yes.
Yeah. So we have initially discussed, I think. Mm. So if you see here, we have already discussed what is the extensive properties and what is intensive properties. So intensive properties is nothing but the properties which remain constant. Extensive properties is the one which multiplies by the scale of the system. Okay, so you need to remember these two lines. Intensive means whichever remains constant over all the system, and extensive is the one which will multiply by the scale of the system. Okay, and if you come to that question, yeah, so if you see it here, first we'll go from the options to this. So they have said that okay, we have the temperature option. So we know that the temperature of the file will always be intensive property because it will be remain constant over all the system. So then only we can do the experiment, right? So it will never be the extensive property. So we will need to go for the temperature intensive property. So there are two options. One is temperature intensive here, and one is temperature extensive intensive here. And we will come to the question. A batch process for the recombinant production of hyaluronic acid by Lactococcus lactis on a high glucose medium is run at 2-liter bioreactor. So here they given the volume. The bioreactor is maintained at the temperature. Okay, they are given the temperature. Biomass and hyaluronic acids are see here they have the two things. One is biomass and another one is hyaluronic acid. Yeah. So yeah, or unless using the samples collected at the end of the experiment. The hyaluronic is a class of, so they are mentioning which is and high viscosity. Okay, they have mentioned that it is a high viscosity. Which one is high viscosity? Hyaluronic acid is. So they said that hyaluronic viscosity has the higher viscosity. Identify the correct intensive properties and extensive properties. So we know that the volume will change. So volume will always be the extensive property. Temperature will always be intensive properties. Uh, yeah. And can anybody tell me will the density will be the, so here we have only two options which says the temperature and the intensive properties. So yeah, we know volume is a extensive property, mass is also extensive property, it will vary. We'll come to the chemical expansion. Can anybody tell me whether density will be intensive or extensive property?
Intensive.
Yeah, so density is intensive, so it will never be the extensive property because the density of water molecule is fixed, right? 1 gram per cc or 1000 kg per meter cube. In the same way, if you increase the water molecule, because the density is a specific molar density, because we will divide the number of molecules, so it will always be the intensive property. The chemical composition is also always be the intensive properties, because if I take water molecule, to give it in a good example, water molecule chemical composition will always be same irrespective of the stage. So that's why it will be intensive property. So the correct option will be D. And you understand the question, right? I think.
Yes, sir.
Yeah, thank you. And then this is another one. So just read the question and understand it. So here they didn't talk about any volume, temperature, or anything. Just understand the topic. So so can you give me the answer for this question? So the question says that necrosis is one form of the uncontrollable death of the cells, which results from the severe environmental stress causing cell swelling and cell lysis. Which state variable from below can best describe the cell death? So what is happening was, uh, okay, so if you can tell the work done, because there is some work is happening due to the necrosis, we are having the uncontrollable death of cell, which results from severe. See, what does it says here was, uh, this is just imagine output, and there is a death of the cell is happening. Uh, that name of this is necrosis, which results from. So how does it arises? From environmental stress causing cell swelling. Okay, so there is a initially one cell is there, due to the environmental stress the cell has been death through cell swelling and cell lysis. So what is happening here was, there is something happened from the change of one position to the another position. Okay, so what is happening? So it is happening in the forward process that the work has been done. So it is that the system has changed from its initial position to later position due to some work happened in this system. Okay, you can think that there is a work done. Okay, the work is done, but you need to understand it in the different format. Like the question, see, there is a cell death happened, and there is the initial cell, and the initial cell has, through the necrosis, by the necrosis the cell has gone to the uncontrollable death of cell by environmental stress, causing cell swelling and cells. So I will put it in different terms. The A system has gone to the B system. A has reached the B through the work done by this one. So basically it is a clear example of the entropy. You understand what I'm saying here? Hello. Hello.
Can you explain how it is entropy?
Yeah. So okay, there is one point A, and there is one more A to B. So what does the entropy difference says was, the amount of heat carried from one point to another point to change its form. Okay, so suppose you have taken the chalk piece. I'm just giving one basic example of this. So you have chalk piece which is in the A form, which you throwed. Okay, you thrown it with certain speed, and it breaks into small pieces. So what is happening here was, so there is a movement of disorderness of the system. So this is the system which got disordered by the force applied by you, like the throwing or whatever you did. So what it was it happened through the time. Okay, it can't be irreversible. I mean, it can't be the backwards. So basically the entropy definition from here says that when the system from one position to it changes to another position, through the work happened by external forces, and we need to understand that entropy, it is a movement of disorderness of system. So if you take in the work done, so there is no work done here, right? And if you take the heat content, so there is no statement saying that okay, due to the heat release this was done. And if you talk about the internal energy is about, say suppose I may have considered the internal energy if they are given the statements like okay, the cell possesses this much activity, has been reduced to this much activity. Okay, but what happened here was the disorderness of the system has been occurred. Okay, you can see that the system which was in the living form is gone to the death form. So the movement of disorderness is one of the point which you need to notice, and another point is it is in the time process which is in the forward reaction. So by these 2 points, and you can say that okay, there is no work done here. The work done was uh, how to say it. So work done, you can tell that okay, if I have one reservoir, you are sending some energy into this reservoir, and this reservoir has given some electricity. Just assume it like this. You are giving some energy, it is converted to the electric force. And just I am giving out of some example, work done. So here you can say that okay, here the work has been done. Okay, the entropy is that the system has converted from one form to another form by the work happened. I think you got the point.
Yes, sir.
Yeah. In the next class, maybe you will understand better when I am talking about the how to convert, how to link the internal energy with the entropy. So basically, you need to understand that work done is that when you are giving the two systems and the process which at the work. Suppose here, if they given some system saying that here, okay, I have given some. Say suppose I am giving some environmental stress, okay, and from that stress, this see if they said that the cell has done some work and this is the output. Say suppose they said that okay, how to say it, say suppose there is a tumor, the tumor has occurred into the body, and there is some energy happened in the cell which gives non-tumor. Okay, I can give it like this, sorry, uh, sorry, yeah, my bad, yeah. So there is a tumor in our body which went into the cell, and it comes out as a non-tumor. So what it done was, there is some tumor attacking on the cell, which the cell reacts. The cell has done some work such that the tumor has become the non-tumor. So this thing, then you can tell what is the happening in the cell was it is doing some work. But if you see the whole process, the tumor to non-tumor, it is the entropy. It is changing from one form to the another form. This is some lame example, but I think you understand the point of the work done and the entropy.
Yes, sir. Understood.
Yeah, thank you. And yeah, this is the third question. So can you give me one answer? So why I gave these three questions was remaining all questions which you can be uh, seen in the class, or if you say zeroth law, the first law, second law, or the what is Helmholtz free energy, state functions, path functions, triple point of water, that I explained through the concept, and there are few questions which need to be addressed as a problem. So that's why I have taken these three questions. So can you give me the answer for this question? So I will make one diagram meanwhile. Yeah, can you give me the answer for this question?
So 130 joules.
Yeah, it's correct. So can you explain me like what has you have done? Like there is another student, right? So at least, so So the both of you got the 130, or if somebody has 270 or minus 130. So I will explain this question like basically. So what they said was the answer 130 is correct. So what they said was there is from state A. So initially, so as we discussed, say suppose here we discussed. So here we discuss the state problems, right? So this molecule is also in the equilibrium, and this is also in the equilibrium. So you need to remember one thing: whenever you are discussing about thermodynamics, unless until they mention, it will be in the equilibrium state. So yeah, it is in the A state, which was moved to the B state. Say suppose A is here. I'm just giving heads up. B is here. So this is A state, and this is B state. And so from going from A to B, there is work of 200 joules has been done, and into the system, and the system is B, and the sorry, and the B has done the work of 70 joules. So if I talk about the internal energy is nothing but the energy coming from out onto the in. So U equal to Q plus W. So here Q is 200, okay, plus bracket. So it will be minus 70, because you need to remember that when the energy comes into the system, it will be plus. That is another thing. When the work is done on the system, it will be positive. Work done by the system will be negative. So this is the thermodynamics notation you need to remember. So it will be, sorry, missing it. So it will be 130 joules. So as here they say that the system does work off. So does work means it has sent something out. So it means work done by the system. So that's why we have taken the negative value. If somebody has said that okay, the work has done on the system, okay, if they given some another work saying that okay, say suppose we have A and we have another system, and from here it has done some work, say suppose it is C, D, and D has generated some work and it has a come, then it will be like, for this it will be minus, for this it will be positive. Okay, so that's why the answer will be 100. You need to understand that whether the while answering this type of questions, it's better to make one graph like this. So it will be better clear. Say suppose if you don't make this graph, you may think that okay, basically the equation will go like this: internal energy equal to Q plus W. So you will think that okay, it is 200 plus 70, 270. But once you make this diagram, you will understand that okay, there is something coming in and something going out. So the whatever going out should be the minus from whatever coming inside. So that's why the answer will be 130. I think I'm very clear in this point. So everybody understood this point?
Yes, sir.
Yeah. So this is for the first week. I think this PPT will be shared with you. I think yeah, the PMRF team will share the PPTs. If you have any questions regarding the research or the thermodynamics, you can ask me. Yeah. So if you had any questions regarding the PhD in IITs, or any like regarding the regarding the PhDs or IITs, or the one with the thermodynamics, or how can we implement the thermodynamics in your own way, like say suppose you are doing some other experiments, if you want to understand thermodynamics in a better way, you can ask me. If I don't know, maybe I will let you know by the uh, next week tutorial class. So let me know if you have any doubts. Okay. So yeah, if you have any doubts, you can have the session. So you understand the topics, right? The what is extensive properties, what is the intensive, and all the things. If you have any questions regarding the zeroth law, up to zeroth law, because we are not talk about the energy, because once we go on to the energy, it will be the terms like there will be terms of internal energy, and as I said that, right, we have four postulates. From that four postulates, we have this thing, what do you call, four laws, and then we have the postulates. Why the postulates were developed was what do you call, to elaborate the system with more in the terms of entropy, temperature, and these things. So that's why they have done uh, majorly for this reason. So yeah, so we'll let you know. I mean, once you go into the internal energy, there will be more of derivation part. Okay, to understand that. Okay, why and basically, see, thermodynamics initial it will be all with the guesses. We need to assume that okay, the system is following this rule. Then only we can solve it. It's not like that. Okay, I need the proof saying that. Okay, how can you say it is zeroth law? So the system has said that it is zeroth law. Then from that point we can prove it in the reverse way. Okay, why can't it be? But we can't question that why I should use it. So this is another one thing which we need to think about it. So yeah, if you have any questions regarding the zeroth law or the NPTEL course, you can ask me. So if you don't have any questions, I think we have 10 more minutes. Uh,
Sir, when we will be having the next section?
it will be on every Tuesday. Every Tuesday, 6 to
Okay.
8. Yeah.
Okay, sir.
Yes. So I think this PPT will be shared. I don't know whether I think yeah I think they will share the PPT with you as a whole. I need to check with the team, and yeah, if you have any questions, you can drop the question in the discussion form. I will see like once in at every evening or maybe 2 days once. I will see the question and I will let you know the answer. If you have any doubts, I think there is a discussion form in NPTEL portal regarding the course. So there you can ask the question. So from there we can have the chart saying that okay, if you have any questions regarding the equations, say suppose uh, beforehand, say suppose in the from the next sessions, if you have any doubt saying that okay sir, how to there is a doubt in the Euler relation or the Gibbs-Duhem equation or the Maxwell equation, if you give me heads up saying that if you have the discussion form, okay, so how it will be easy, because I think by going on, if there are more students, it will be easy if you have predefined the questions which you have. It will be easy to interact directly through that point. So I think you got my point what I'm saying. If you're having any doubts, you can go through it, and I think in the further next classes there will be more of equations. So in 2 hours it will be very difficult to cover all the topics. So I will go through like what are the assignment questions you have, and what is the basic things which you needed to fulfill that. And if you have any further like in-depth analysis if you need, then you can put it in the discussion form, so that we will discuss on the next class, on the next session, interactive session, so that we can do. Okay, so yeah, thank you for attending the session. I think we can close the session, and thanks for coming and thanks for asking the doubts. I think you understand. I think you. I hope that you understand the topic. And if you don't understand, then please let me know. I'll explain it further in the upcoming tutorial classes. So thank you.
Thank you, sir.
Okay, thank you.
Thank you, sir.
Oh, thank you.